I'm John Wilker, the organizer of 360 IDEP. I hope you enjoy this session recording, but first I wanted to mention one thing. We've served the community since 2009, and over the past few years we've had to take on debt in an effort to keep the conference alive. After several unforeseen challenges, not the least of which is a pandemic of indefinite duration, we've had to make the hard choice to end the conference as we're now facing over $100,000 in debt. As a result of requests from the community of how they can help, we've created a GoFundMe campaign. If you're inclined and able, please consider donating to help keep 360 IDEP going. The QR code after this will link you to the campaign. Thank you. Enjoy the recording.
So thanks for coming to Structured Concurrency. My name is Ash, and welcome to the Android conference. You might be going, this is not an Android conference, but I actually teach iOS and Android in one class. And by the time I'm done, the students they're so fluent in both that they have absolutely no issue thinking of them in the same mental model. Actually have a ton of apps up on the App Store. So my favorite one is this Photo Do, and I was going to give a demo, but the screen capture won't capture. So basically what happens is you pull out your phone, and it makes a to-do list, and you don't have to use any typing. You just talk into it, take a photo, and it makes a to-do list for you. So again, I'm really big into Android, 7 apps on the App Store, fun stuff. We went, on the Android side, we've gone through an absolutely huge change. And we used to work in Java and XML, but now Google is teaching everybody to use Jetpack, Compose, and Kotlin. When you talk to Android developers out there, a lot of them don't even want to move to Kotlin, and they don't want to move to Compose and build things like this. But the writing's on the wall, right? The writing is on the wall. Google is publishing, if you've never programmed before and you want to be an Android programmer, learn Compose and Kotlin. Okay, let's just stop and think about that for a second. Google is telling all new Android programmers to learn Compose and Kotlin. If that's not a red flag to say Java and XML is kind of going to go away, I don't know what else is. They're bringing all the new people, hey, we're Compose, we're Kotlin. Well, then when they go out to get jobs from the new libraries, anything that happens, they're not going to know Java and XML. Don't think Google cares, right? They've set their path. Not only that, but a lot of people on the Android side are using Compose to drive UIKit, right? So what the Android community is telling everybody is if you work in Compose, you will never have to learn iOS development because we will generate everything you need as a iOS developer through our toolkit. There's only one problem with that, right? They're building for UIKit and Objective-C. I personally have issues with that. And I wanted to give you guys my viewpoint. Could be wrong, could be right, but at least you've heard my viewpoint. So I flew around the country, and this is back in 2020, and I was telling people, you probably want to really get over to Swift. You don't want to do Objective-C anymore because this is the beginning of the iceberg, right? There's things that Swift is going to be building on that when you're on the language, it's going to make life a lot easier for you. And this was before Swift UI. A lot of people said, no, Objective-C is not going to go anywhere. All Google builds on Objective-C. Even today, Google builds completely on Objective-C. But I said, just look at the handwriting on the wall, right? At WWDC 2021, they had, if you grab all of their code, all the words on the website, right? Objective-C showed up once, and Swift showed up 103 times. The word UIKit showed up 8 times. The word SwiftUI showed up 43 times. So even knowing the Android community is building to UIKit and Objective-C, I think they completely missed the mark. And it's really interesting as time evolves, we see a slide coming out of WWDC that says this. the best way to build an app is with Swift and Swift UI. Well, okay, I'm kind of embellishing because that's not really what they said. What they said is if you're new to iOS, the best way to build an app is Swift and Swift UI. I kind of embellished and say the best way to build an app is with Swift and Swift UI. And the thing for us is, when you look at our architecture, how we build Android and iOS apps, they look almost identical because we're building the same mental model for both of them. And one of the things is, I'm big on Combine, right? I built an entire course for Springer Nature, Apress, that explains what Combine is. So I'm big on Combine. But I'm also big on not using Combine ever again, right? Because I tweeted out, we're not saying that Swift Structured Concurrency is going to replace Combine framework. They're different. One's about threads and one's about publishing. What we're saying is, just like Kotlin added flow and channels, Swift Lang will now also implement flow. Now, I'm not saying that it's going to replace it, but I am saying it is going to completely replace it without saying it's completely going to replace it. So as Swift evolves, and we're going to get into this in the playgrounds, you're going to see it's been doing a lot of things that Combine used to do. And as time goes forward, I truly believe, just like Kotlin took over all the publishing from the reactive network, Swift will also bring in all reactive programming into the language. So the question, what does that mean to us? That means that when I'm giving a class on iOS Android development, the file system is exactly the same for both projects. And a lot of people are like, so what, the file system is exactly the same. But if you take a step back and you think about it, if you know one, you know exactly what file to go look at the other one, exactly what that file is going to do, exactly what that purpose of that file is. So if you know one file structure, being able to go to the other file structure and looking at it, it's exactly the same, makes everything like a duck to water, right? Because the file structures are the same, that means that the way that things are hooked together are the same. And Compose UI looks a lot like Swift UI. Kotlin looks a lot like Swift, which means that we're able to have the same clean architecture, the same CI/CD, building the entire same app. And I think that for now, I haven't brought in on Kotlin multi-platform because they're on UIKit and they're on Objective-C and there's some other memory models. But this sets us up, right? Say one day JetBrains gets it, right? They get that they're going to Swift UI, they're going to Swift, and Kotlin multi-platform is the way to go. Well, Kotlin multi-platform is just the Android app we're building. Nothing on that side changes. And if they get the Swift UI piece built with Compose, it's a duck to water to move our architecture to theirs. So I'm future-proofing by building on Swift UI and Swift Structured Concurrency. And if you look at our apps, like this one is a app, and I open sourced it. You can see it on GitHub. But basically, what it does is when you rent a bike, it turns into an exercise, and all that exercise information goes into your Google Health. So the more you rent bikes, the more exercise you get, and you can turn these into NFTs. And then NFTs get you like a patch. Like if you save 500,000 carbon units, you get this patch, and you can't buy the patch. The way you can get a patch is by saving carbon units. So let's see here. Okay. A lot of the stuff I'm talking about is covered in this article I wrote on Swift Structured Concurrency. And it's not as well detailed as it should be, but over time, I think I'll be adding to it that it kind of makes more sense. But I just wanted to point that there is this Medium article that I am working on that is going to cover how Swift Structured Concurrency works. So there is a GitHub repository that I've been sharing on the Slack channel. I keep making changes to it, so hopefully you guys have the latest version and you can play with what we're doing. If not, you can just listen to me I'm thinking that because this is all screen captured, we're going to do a bunch of lecturing, and then toward the end, we're going to play with the playgrounds. Now, to get into Swift structured concurrency, I kind of want to start off with talking about how does do, try, catch works. Because when I try to teach this stuff, there's some basic concepts that students get caught up in, like they'll do 15 tasks and only the first 2 run, and they don't know why. And I'm like, well, your second task threw an error, that's why the rest is. So understanding this stuff is going to help us with Swift structured concurrency. So a little bit of history. We have the old way of handling errors, where we would call a function, and then what would happen is we'd return a tuple. We'd either say, here's the data, or here's an error. This is really ugly code to work with, and even at the call site, there's just all this boilerplate ceremony code that you have to write to be able to handle these errors. I just think this is really ugly programming. Really didn't like it. We evolved a little bit, and then we, in Swift 5, we got a result type, right? Again, on the result type, we had some ceremony to go through to be able to get the result out, and we have to go through this case statement to either get the result or the failure. And I put this all into a playground, so if people are a little bit hesitant about how do catch works, just go in here and you can just move make this a false, make this a true, play around and just see how it works. But what we really want to do is we want functions that throw. And when we get into Swift structured concurrency, we'll see that's when things get really beautiful, because you make a function call. If you have an error, you just throw. So, this is a function that throws, and it's either going to return a title or it's going to throw. We have 2 of these. We have a title 3 and a title 4. And I want to show what's the interaction like when you have 2 throws right after each other. So, okay. When we call this get try 3, we're going to put the results into the new title. And if it works, we're inside this do loop. So this do loop will catch any errors. And as soon as it catches an error, it's not going to execute the rest of the do loop. It's going to immediately call the catch. So we don't have any errors right now. What did I do? Yeah, so everything runs extremely cleanly. But if we make the first one, what happens is, as soon as it sees this error, it does not execute the next code. It jumps straight into the catch. So if we're doing like a task group, when we talk about Swift structured concurrency, and one of the tasks throws an error, the rest of them won't be caught. And it's not because Swift structured concurrency is complex, or it just comes back to how do catch works. So I'm just trying to point that out here, so when we get deeper in, people aren't like, wait a minute, why isn't this running along? Now the other thing we can do is if we put a question mark on this guy, that's basically saying that function does not try. It doesn't try. There's no such thing as try on there. And so when it runs, what we see is it just doesn't appear anywhere, right? It just never happened, and we went on to the next one. Where if we don't have this, we don't see title 4 because this threw an error and we immediately went to the catch, right? So that's one of the things to realize. If you need to get to the statements, depending on the order, you get to some statements and you don't get to others. So that's something to think about. Or what you can do is you can break them up into different do loops. And that will guarantee if one throws, then the other one will still be executed. And again here, if you put a question mark on any of your tries, you don't have to do a catch because it's basically saying that that function does not throw anything, and you just get an error here. Now, one of the other things is if we have I'm going to put this back to true. And again, I put all these into playgrounds so that during our break, you guys can go through and play around with these. It's really easy to reason about what's happening. The functions are first written, and then the variables to be able to change them from true or false are written, and then the actual calling code is written. So feel free to go and play with these to figure out how these pieces work. Now, let's see. Catch, validate. Okay. In SwiftUI, you always want to return something to the user, right? So all errors, like we got this from the Combine framework. When Combine publishes to SwiftUI, it never fails. Because if you're publishing to your UI piece, the problem is that you've got to show the user something. So when Combine's talking to SwiftUI and it gets an error, that error has to be turned into a string, and that string goes up to the UI, right? That way, from Combine to the SwiftUI view, the user isn't left hanging. So in Swift Structured Concurrency, if you get an error and you're talking to SwiftUI in the main thread, turn it into an error and send it out. So here we have this error will always turn into some sort of a string that we can put on the main thread and we can give to SwiftUI. Now, one of the last things I want to point out is throws, right? If you have a function that is trying and it's throwing errors, you do not have to wrap it in a do loop, right? If you're throwing, you don't have to handle any of the errors that are being thrown. Now, this is really interesting. There are other languages that don't force you to handle your errors, which a lot of people go, no, you should always handle all your errors, right? If you don't know how to handle it, just throw it. But if you talk to people who design languages, what you'll see is they say, okay, I'm at the OS layer, right? And I'm trying to get an inode, and I'm pulling on this inode, and I don't know there's no way I can not get an inode. And now I'm not getting an inode is like how you describe a block of sector on the disk, right? So I'm the operating system, and I'm going and I'm trying to get a sector on the disk, and I get thrown an inode error. That's insane, and that should just never happen. But on the operating system, I don't really know what to do with that, so I throw it, right? Well, that goes up into the disk utility. And disk utility is like, why? I don't know what to do with this inode. So he throws it. Goes up into the repository. The repository is talking to networks, it's talking to disk. It doesn't know what an inode is. It throws it. It goes up into the UI layer. What does the UI layer know about anything, right? The UI layer is thin as, the UI layer does nothing but show the UI, right? So no one else caught it, it gets thrown up into the UI layer, and the UI layer is looking at this inode going, no, right? So there are languages out there that don't force all throws to be caught, but Swift does. And if you throw it, the person above you's got to catch it. And here we can see that if I remove this throws, then we would have to uncomment the do catch. That took a long time, but it's just super important to understand how that works, because when you layer Swift structured concurrency on top of it, it gets too complex. So now, before we get into Swift structured concurrency, we have to understand the memory model of how programs run. So we actually use Backblaze for our backups, but they actually wrote this little article talking about how memory management works on programs. So here we have a single-threaded program, and we have a multi-threaded program. So the heap is where we keep all of our variables, right? It's memory, and we can allocate it, and we can deallocate that memory, and we put all our variables in there. The stack and the registers are what's running through the CPU, right? just think of the stack as a constant. We don't want to mess with the stack. We've got stack pointers in there. And if we start moving around in the stack, it's going to corrupt our pointers and everything. So our mental model is the registers in the stack. Everything in there is a constant. And then when we have multiple threads, what we have to do, because the stack and the registers are specific for that thread and we don't want to move them around, we make a copy of the stack and the registers for each of the thread. The heap is shared between them. Well, this causes a huge problem, right? Because if you have one heap for multiple threads, how do you handle that synchronization, right? It can get really, really tricky. The beautiful thing about working on the stack is every single time you're doing anything on the stack, it makes a copy of it. Now, iOS is a protocol-oriented programming language, right? Which means that we're always working with structs and we're programming to protocols. It's beautiful. Like, I wish Kotlin and Python and all these other languages I work with, I wish they had this idea of being a protocol-oriented language with the main construct we use is struct. So we always try to reach for a struct whenever we can, because we can thread all day long and we're not going to have any threading issues. Where that heap is shared between all the threads, those threads are going to be clobbering that shared memory constantly. So let's talk about a little bit about the different pieces. So value types are structs, enum, strings. They're thread safe and they're stored in the stack. Reference types are when you make a copy of one thing, you just get a pointer to it. So when you make a copy of a struct, you get two completely different structs. If you make a copy of a reference type, you just get a pointer that points to it, right? Classes, functions, actors, they're stored in the heap, and they're not thread safe. So what do we have on the stack? On the stack, we're putting our stored values, right? And each thread has its own copy. And what are we putting on the heap? We're putting our shared resources, our objects. So structs are values. Classes or references are sometimes called instances. And you can think of an actor when you get deep into actors, but you can think of an actor as a class, a thread-safe class. We're going to be using structs for our views, our data models, almost everything we want to do with a struct because it's safe. Our classes, there are view models. Why? Because view models have to be shared. It's a part of being observable, and we're going to get a little bit deeper into that. And then our actors, those are the classes that we need to be thread safe. So any managed state, shared data, data stores. The way you make an actor is instead of just writing the word class, you write the word actor. And that is thread safe. And we're going to get deep into that at the end of the talk. But right now, I just want to set the framework of how things work. Again, our observable object, this requires that this be a class. There's just no way around it. So all our observable objects are classes. Now, when we make a class, and the Colab goes, I said Colab. Okay, so I'm going to be saying Colab a lot. Colab is a Google tool to build ML models in the cloud. And I do that all day long. So I work at a biotech doing machine learning, and everything I do is on a Colab. Like a playground, but you do machine learning Python code in it. So if you hear the word Colab, just change it to playground. So in this playground, we have a class, right? In this class, because it's a class, we have to have an initializer, and it's going to take us a title, and we're going to be able to update that title. So when we make that class, we're going to give it a title, and then we're going to take that class, and we're going to make another class. Now, when I said make another class, wrong. Not make another class, right? I said that on purpose because now I can just really explain. This is just a pointer. This is a pointer to the same class. We did not make another class. We didn't do anything. We just made a pointer. This thing and this thing are exactly the same thing. We didn't do anything. We just made another pointer. So we now have this object A, which is now called object B because it's a pointer, but it's still object A. And we're going to change its title. And when we print object A and object B, we get the same thing because there's no difference between these two things. It's just like, my name is Siamak and my nickname is Ash. Still the same person. It doesn't even mean anything. In fact, if you took my nickname off, nothing changes. So here we have a second class, and in this class, what we're going to do, where's my class? Okay, so my class is a var on a string and a title, right? And let's see. Okay. So here, I'm going to make my class, and I'm going to give it a title, right? I'm going to print the title. Again, I'm going to change it. I'm going to make a pointer to it, and then when I change it, it's going to change out both of those. Sorry, I went through that. Let me see that. Okay. I make a class, and when I set the title, that's fine. Okay, sorry. When I make a second class, these two classes have nothing to do with each other, right? This allocates the memory for the first class. This allocates the memory for the second class. And now, because they're completely two different classes, I can just manipulate them as much as I want without any issues. So if you want a class and you want to be able to manipulate it without touching the other class, just make two of them. Great. Now let's talk about structs. Right? I have a struct here, a var struct that has a var for its string, and I have a struct here that's a let for its string. The thing about structs is that they live in the stack. And one way that it was explained to me, in our mental model, we have to understand that when these things live on the stack, if we say var here, what we're basically saying is if you change it, completely destroy that struct and put another one on the stack. Now, what's interesting is in Swift and Swift UI, it's not quite that easy to think about because we have @state and @published, which allows us to change a struct without changing the actual underlying. And Swift is super fast at making structs. So it's true that in Swift UI, when you update the struct, it tears it down and builds it, but it does it really efficiently and very quickly. But in our mental model, what I want us to hold is, when we make a struct have a variable in it, or we make that struct a variable, if we change anything in that, it's just like making a new struct, right? So here, we have a struct that's a variable, and we print the title, and we make another struct, and we print the title. If I were to change one of the struct's titles, you notice it makes no difference to the other struct. Because here, each struct is in its own separate part. And so structs, unlike classes, they're not shared. So here we have a struct called custom struct, and we can call update title, but it's just going to return to us a whole new struct, right? Again, we get a whole new struct. If we have a mutating struct here, and we have a mutating keyword on the update title, it looks like we can go into that struct and just update that title, but it actually is going to tear down that whole struct and just make a whole new struct for us as the mental model that we really want to get a hold of. So when we make our struct right here and we give it a title, we have to call it, we have to put, make sure that put a variable here. Because if we put let here, then we won't be able to change the title. And here again, when you go through and play with this playground, you can try making the struct a variable, making the title a variable, and seeing how this interacts with allowing you to change it or not change it. But basically, the only thing I really want you guys to get out of this is that every time we change a struct, we're basically just going to be building a brand new struct. And so one of the key things, interesting thing here is we put the word mutating on this struct, right? Because what we're going to be doing is changing something that we say is immutable. This is not for the compiler. The compiler doesn't need to see this. This is basically telling the developer, hey, developer, you do realize you are making a struct that we would like to keep immutable, and you're trying to mutate it on it. So anytime you see the word, escaping, or weak self, or mutating, those are red flags that we're probably trying to do something the language is not happy with. And we're going to get deeper into those in the next collab. But here, again, I just wanted to show what an actor looks like. And the actor, when you change its title, make another reference to it, change its title, it acts exactly the same way the class does. So when you think of an actor and you think of a class, they're basically the same exact thing, except an actor is going to be thread safe. And I'm going to get into actors and messaging, but I just wanted to get everyone on the same page that when we're talking about something in the heap, it's shared. When we're talking about something on the stack, you can think of it as isolated to that thread. When you copy something in the heap, you're making a pointer. When you copy something on the stack, you're making a whole new copy of it. So structs are wonderful in their immutability. And that's why we are really fortunate to have them in this language and make extensive use of it, because immutability is very important in programming, concurrent programming and programming. Now, before we get deeper into how tasks work, I wanted to tease this up just to show you how beautiful they are. So you're not going to understand a single line of code I'm going to show you, but hopefully you're going to appreciate its simplicity. And then at the end of the session, you're going to look back at this and go, wow, that really is beautiful code. Okay, so in the olden days, which is now currently, if we wanted to get an image from our server, what we have to do, let me turn this off because this URL we're using can only handle a certain number of requests before it says, you asked me too much. Okay, so in the olden days, what we would have to do is we'd have to say, okay, I want to get an image. Okay, how am I going to do that? I'm going to get off the main thread and get onto a background thread because I don't know how long it's going to take me to get this image. So I'm going to get on the background thread, I'm going to go out to the server, I'm going to grab the image, and then I got the image, I rebuild the image. Now I want to go back to the main thread so I can put it up on SwiftUI. I'm going to show you how to do all that in one line of code. Actually, it's like 10 characters. And this is what's important, right? So Swift structured concurrency is not just touching how we build algorithms. It's not changing how Apple is building their algorithms, because they have retooled all their algorithms to work with asynchronous calls. But they're retooling their UI to work with synchronous calls. So we're really looking at the tip of the iceberg of what's going to come at WWDC 2023, 2024, 2025, 2027, right? They're going to keep driving this model. And it's going to get easier and easier for us to code. But we're not going to be able to use Grand Central Dispatch. We're not going to be able to use UIKit. We got to move forward. So the old way, right? So we have this handle response, right? We're going to give it our data and the response, and it's going to give us back UI image. So we're going to be using this handle response. Now, this is the old way we used to do it, right? All three of these calls are going to use URL session with the handle response. So here, this is the URL session that we're currently using. And we give it a URL, and we have to give it a closure. Now, what we mean by escaping is this closure will outlive this function. Duh, right? Of course it's going to outlive this function. This function is going to be done, the iPhone has 2 billion transistors. It's going to be done with that, I don't know, fast. So this closure is going to outlive the function that called it. And there's a lot of talks online you can go into, and they talk about why that's a bad idea. You really don't want your closure to escape out from the function that calls it. So again, anytime we see the word escaping or weak self, we really want to worry, any of these guys. It's just like we don't want to architect our code this way. Weak self is basically saying don't increase the reference count, right? So in this example, what would be is the user goes and says, I want to see this image. This closure captures the image which is outside the closure, so we have to call self to ourselves, and then I have a hold of this UI placeholder. Then the user scrolls away from the window, and what happens is I'm still going to try to get that image. But if I called weak self, then I know that the user doesn't want it anymore, and I will let go of that resource. And another place you would see like weak self is if you have a house and an owner, you would put the weak self on the owner's house. Because if the owner dies, the memory system will not let go of the owner because the house is pointing to the owner and the owner is pointing to the house, right? So what happens is you have a strong reference cycle. And if you put weak self on it, if the owner goes away, then the house won't keep a reference to the owner, and it could be freed out of memory. So that's another place you would see weak self is when we build strong reference cycles to objects. So here, we really don't want to be working with escaping. We really want to be getting rid of that. Now, as I mentioned, I taught combine. I love combine. But here, even this is hard to work with, right? Because our URL session is now a publisher, and then the response that we were talking about is going to get mapped, and the error is going to get mapped, and it's going to be returned to a publisher. Still not. I mean, when I taught combine all those years, I said this is really, really wonderful. It's because I was looking at this, but now I just think this is horrible. What I really want to do, right? What do I really want to do? I want to call my function, throw to me if you have an error, or just give me back an image. That's coding, right? That's what we want to get to. That's where we want to be. That's where I am today, right? Get me an image, right? Get me an image. Take as long as time as you want. When you're done getting the image, give it to me. You know you got a problem? Throw it, and I'll handle it, right? So this is the beauty of URL session shared data that has a ability to be called from structured concurrency. We're going to get into how all this works. I haven't explained any of this. I just want to show you how beautiful this code is, right? So we just call the URL session with the URL, and we get our data and our response, and we can give that to our handler. And so let's see what that looks like when it runs. So when we get a chance to play with the playground, you can come in here, and we have this asynchronous image view, and what it's in a VStack, and at the end of the session you'll understand how this works. But right now, just know that we're calling the download with async inside a background thread, right? So it's going to call this guy. When he calls it, we have this. We have SwiftUI watching the image, and when the image changes, it's going to update that image. Really, really nice. So we went from using URL session inside handling a closure, taking in a closure, to simply being able to call it on a background thread and getting our image. But it even gets better. Like I was saying, right? This is the tip of the iceberg. Inside SwiftUI, you can just say async image. Don't have to worry about any of the background threads, escaping closures, none of it, right? You just call async image and give it the URL. And it's going to say, oh yeah, okay, I'm going to get you the image. If there's a problem, we're going to run it. So when we run this, Notice the line comes up blue, which means it was able to find the image. And then once it loads it, my Wi-Fi is horrible, but there it is, it just loads the image. And this is really this is really why we're here at the talk, is because, WWDC 2027, this is what we're gonna be working with. Not only that, let's say I wanted to make an image viewer and put that up on the iOS store. How many lines of code would that take me? 3. Great. With 3 lines of code, I can make an image viewer, which is this guy down here. Basically what I do is every time I hit this URL, it gives me back a different image. And I have this little task running that every 4 seconds, I call this async image and I get a new image, right? So with maybe 5 lines of code, I made a nice little app I could put up on the App Store, and I could just enjoy random images on my app. Super, super powerful stuff, couple lines of code. What do we have to do before? We're on the main thread, get to a background thread, hit the server, escaping closure could cause issues. Maybe we get an error, maybe we don't. Come back from that, maybe have to handle the error because inside a pyramid of doom, because we have closure after closure after closure, and we can't handle any of that error. And then that image comes back, and then we have to go back onto the main thread and then put it on SwiftUI. No. We just go async image. So I know you guys don't understand how all this code works. We're going to get into it. But that's the beauty of what we're talking about today. So, yeah.
Quick question.
Yeah.
Back on your async image view, not down too far, way down.
Yeah. Yes.
What above? Async image view, one above that, a little above that, function above that. Your task.
Yeah.
When you're done, that image equals downloading. What thread would that be on?
That's a very good question. We're going to get into that. And the answer to that is, it probably starts on the main thread, but when the system doesn't want to utilize the main thread is being utilized too much, it'll be moved to another thread. So we actually have a playground where we show when you start tasks, where are they going? And so when we get to that playground, you'll see it starts on the main thread, moves to a different task, or maybe it just stays on the main thread depending on how busy the system is. But the system handles all that for you. Okay, so let's talk about why I hate escaping closures, and closures in general. So I have this function, and I'm trying to read it. I'm trying to teach this to students. And I go, you have this fetch weather history. And you look at it and you go, what is this thing returning? I really can't tell what it's returning. But it looks like it's taking. It looks like it's taking this. It looks like it's taking this escaping thing that accepts an array of doubles, but it's escaping. I don't know. I don't know what it's returning. I don't know what this is doing. Very confusing. But it looks like when I give it to the completion handler, I'm giving these results to the completion handler that I'm getting from here. And I'm running it on the background thread, and I'm just making 100 random numbers, and I'm returning, I don't know, this is so weird. What is this completion, and what's this results doing? No, this is crazy. Don't go like this. What is this? This is a fetch weather history, and it's returning an array of doubles. I show that to my students, like, where do you get that from? That's just what it's doing, right? It's taking a completion handler, and it's returning an array of doubles. And the completion handler is returning that array of doubles. And like, well, why is it saying that it's, I know. And then they're like, okay, what is this thing doing? And they're like, okay, I have a calculate average temperature that takes an array of doubles. I can read that. But then it's got this escaping thing. What is this thing returning? I'm not quite sure what's it. You go, no, okay, look. What it is this calculate average temperatures is taking the array of doubles, right? And it's taking this completion handler. This completion handler is returning this double, so this guy is returning a double. And they're like, their heads are spinning. They're like, okay, one moment. Okay, what does this guy do? This guy takes that double and it takes a completion handler, and what does it return? This string. Like, where do you get that from? Well, how can you read that and say that? Like, that's how it works. And so if we were to break it down, what is this? This function is calling a trailing closure, right? So if you have this function and it's calling a trailing closure, you get to move it outside of the parentheses. So you could write this as a function that takes closure, or you can write it as a function that these two are exactly the same, right? We're just moving the argument outside of the parentheses. But it makes it for funky code, right? Because you're looking at that and you're going, is this a function? Is this making a function? What's it doing? No, it's just a function call, and this is the first argument, right? So at the call site, calling this, right? This is the first argument to this function. It returns an array of doubles, right? This guy is going to return an array of doubles. Where's that array of doubles? It's this, right? So this function is going to return this array of doubles called records. Now, this calculate average, what did this take? It took an array of doubles and returned one double, right? It returned a double, right? Sorry.
That's the problem.
My bad. I even got confused. Okay, sorry. So it takes two arguments. It takes an array of doubles and a closure. So this is the closure that it's going to take, right? Trailing closures. It's going to return a one double, right? So this guy now takes the double and the closure returns a string, right? Now, we're not even dealing with errors in this thing, right? But this is where the pyramid of doom comes from. I know it took a long time to get through this, but a lot of times I'll be explaining how things work and people don't have their heads around closures yet. And so to move forward from what we're doing and people don't have their heads around closures gets really hard. So I just want to make sure we're on the same page, yeah.
Yeah, so ignoring errors, assuming this was 2019, what would you do any different?
It's
2019.
That's what I'm saying, right? So very good point. It's not 2019. So I taught this, right? I taught this. I taught closures forever. If you do JavaScript, you get closures, right? Kotlin, Swift, I think Flutter now, they all have structured concurrency just so they don't have to do this. Flutter is a replacement for TypeScript. No, Flutter is a replacement for JavaScript just so you don't have pyramids of doom. Swift is a replacement. Swift structured concurrency is a replacement for what you would do normally. Kotlin structured concurrency replaces that. So we've all moved on from having to do this, right? Because when you read this, it's really hard to explain to someone. Yeah, I know that this completion handler takes this array of doubles, but that's really what this guy returns. This guy, I know you think it takes an array of doubles, but I mean, it takes an array of doubles, and I know you're trying to figure out what is this double. Well, it returns that double, right? So trying to explain closures, like how they capture their environment and how variables work with them, and how it gets people really, really confused. So let's talk about Swift structured concurrency. What we want is we want to call a function and get back an array of doubles, and that's exactly what we get here. What we want is we want to calculate average temperature with an array of doubles and get back a double. Thank you. That's all. I just want to, when I call upload, I'm going to give it a double and I'm going to get back a string, right? This is what we're talking about, right? Takes away all the escaping closures and all the stuff. It's just easy to reason about what is the code doing. How clean is this, right? I call my fetch weather history, and I get my array of doubles, right? And then I give that to my average, and I just get back my average. I give my average, and I get my string, which is my response, right? And now we're going to put error handling in this, and it's super easy to do it because it's structured code, right? So right now we're not talking about asynchronous code, right? We're talking about structured code. This one line runs, and we wait for the results, and then this line runs, and we wait for the results, and this line runs, and we wait for the results. Now, as soon as we call the task, it starts. But here we have to wait for the results before we can move on. We're going to get, in the next, I keep wanting to say collab, next playground, we're actually going to look at how you would do this asynchronously. Now, if we're throwing errors, like we can see, this fetch users is going to give us an array of strings, or it's going to throw. And we have this save that is going to return to us a string on if it could save or not, or it's going to throw. And to use these, super clean, right? Now, we talked a lot about do catch, just so I can get to this point, and you guys, we covered how do catch works, right? If this throws, we never get to this point. Why? Because it immediately catches the catch. It's what we talked about on the first playground. So, very, very clean. It looks like any other Swift code I write, but this is a structured concurrency. Each one of these is being run on a different thread. And if I have an error, I'm not even looking at it. But here we can easily see that we caught the error and we handled it. Nothing special. Now, we talked about where do these threads go? Oh man, I should do that real quick. Sorry. All the code I'm showing you is produced by Nick and Paul. So as I'm going through these examples, I should point out that, I should have done this from the beginning, but everyone's here now, so it probably makes more sense. These examples are from Nick and Paul. They should get all the credit. I'm just layering on my interpretations of how I would explain them. So, and I changed them up a little bit so that it's just easier to explain. So it's not one for one, but it's close enough. So Nick came up with this really good example of where are these threads running, right? And so we have a little Swift UI view here, and we have an array, and we're going to update the array with the thread that these things are being built on. So here we have Grand Central Dispatch, and we're running it on the main thread. And here we have Grand Central Dispatch, where we're starting on a global thread, but we want to get back to the main thread, so we dispatch back to the main thread. How does that look like in structured concurrency? We have this author one, who is going to be running on a task, and we're going to see what thread he's running on, and then we're going to append that to the UI, so we're going to be able to see it. We're going to wait 2 seconds, and we have another author, and we're going to see what thread he's going to be put on. Then we're going to go to the main actor. And, at the end of the session, we're going to go through what the main actor is, but just the main actor is the main UI thread. We want to play with the UI here because we want to update the list that's in the view. So we have to go to the main, we have to go back to the main UI thread. And we're actually going to make a third author while we're on the main UI thread, and we're going to see where he shows up. So the first task that we calculate, that we generate, is on the main thread. That is our first task. Okay, so our first task that we make is inside of this view. The last session we're going to talk about is how tasks work inside Swift UI. So we're going to talk about what this .task is doing in a future I keep wanting to say collab, in a future playground. But for now, we just know that we are spawning a task and we want to see where it's going. So where does this go? Well, it's being spawned from the UI. So the simplest place for it to go is on the main UI thread. As we run the subsequent, when we add author 1, what we're seeing is author 1 goes on thread number 3, author 2 goes on thread number 5. Now, when we wanted to update these, we moved author 2 back to the main thread so we could update it, and then we started author 3 on the main thread. And here we can actually see, sure enough, author 3 starts on the main thread. Then we wanted also call add something, right? So we're going to add something, and what we're going to see is that add something, again, gets put back on a global thread, but then to update it, we have to go back on the main thread, and we're doing another something, but we're in the main thread, and we see that the second something is back on the main thread. So here you can see we don't really worry about what the system's doing. The system will do what the system wants to do. We're going to launch tasks. Could be on the main thread, could be on a different thread. It could be start on the main thread and move to a different thread. It could start on a different thread, and then we need to move it to the main thread. The only thing we really need to worry about for us in all this is if we want to publish something to SwiftUI, right, we want to await on the main actor, and I'm going to get into this in one of the final labs, but we want to get back on the main UI thread and publish it. But my answer to where is the stuff running is all over the place, depending on what the operating system wants to do, and it's going to get trickier and more complex to figure out what it's doing as we get deeper into structured concurrency, and they find ways to optimize things, and they find ways to concatenate things. So we're just going to let the operating system do anything it wants with where these threads are running, except when we want to put something on SwiftUI, we'll move it to the main thread, or we're going to move it to the main actor. Okay, with all that said, now we're actually going to, for the first time, we're going to start talking about what is Swift structured concurrency. Because so far I've been just giving you examples of why it's great. All right, let me see here. So here we are building this is from Paul, we're building a little bit of function that is going to give us back the weather in London, Rome, and San Francisco, or if we don't know it, it's going to throw an error. So it's going to run on a background thread, and depending on the string we give it, it's going to give us back an array of doubles. I don't want to write this in the closure. I mean, that would just, my mind would blow up. So very easy to do. And then what we have is we have a long-running task that is absolutely nothing more than something to burn time, right? So we just want to burn time. So we do a Fibonacci number. Now, we have this print Fibonacci sequence, which is asynchronous, and it's going to return to us a string. There's two ways to call a task. If I wanted to call a task and just run that task, what I would do is I would use this keyword task, and I would give it the code that I want it to run. So here, I want to start a new task, and I want it to run this async operation. Async operations can only be called from other async operations or creating a task. So a normal function, a normal struct could not call this function because it's async and it has to be on a task, right? So here we form that task, and now we can call async functions. This is async function. If we took this task out, it will complain that, hey, you're trying to call an async function from something that is does not support concurrency. Okay, so we're going to put it into a task, and now it supports concurrency. That's how we can run a function in a concurrent way. But sometimes we just want to be able to make a task and run it at a different time. And here, well, it's kind of the same thing. We say task, right? We specifically tell it what it takes and what it returns. And then we give that to the variable task1. Now we can call task1 at a later point. We can call .result, which returns the result and the value. Or if we just want the value, we can just call .value, and it will return the value to us. So if we look at this, we're going to get an array of integers, right? And we're going to append to that array of integers the Fibonacci value for 1 through 5. So Fibonacci of 0, 1, 2, 3, 4, 5 is this array, and it's going to be returned to us on a background thread when we call this value. And we have to await on this task, right? Anytime we do something asynchronously, we don't know when it's going to come back, right? So this keyword allows the programmer to know that this task is a suspension point. And what that means is we're going to free up system resources, depending on what the operating system wants to do other tasks, because this guy's basically saying, I'm a long-running task, and I don't want to block you. Go ahead and do other work, and when I'm done, you can come back, and I'll have value, right? So this await keyword gives us local reasoning about what this function's doing. The compiler doesn't need this. This is for us, right? It's like, oh, wait, you have the await keyword here? Oh, okay, I know that you are a suspending function. That means that you could be suspended, or maybe you're not suspended. You could be suspended repeatedly, and I can go ahead and do other work here while this is a point of suspension. Great. So that's what that keyword await tells me. I can do local reasoning and say, this is a suspension point. Now, when I go ahead and call it, I have to get into a context that supports asynchronous calls, which I do with starting this task. And then I'm going to go ahead and run the Fibonacci sequence, and I know that it will return to me a value. Now, if we look at this, there's something else running here, sorry. It turned everything else off. That's off. That's off. Task group. Task group is right. Okay. Sorry about that. All right. Sleeping, multi, Fibonacci. So when I run this is a huge point of contention for people who are just learning it. We start the task, right? And then we start the function, and then we end the function, right? What's the first thing you see? We start the function. What's the next thing you see? We end the function, right? This function is done running, right? So right here, at this point, the function's done running. It's left, right? So a lot of times people will start a task, and what they'll do is they'll say, I'm going to use my results at this point of the function call. And it's like, no. This task is awaiting here, right? And so this is a suspension point, which means I'm going to suspend here, and you're going to continue. If we try to use any of the values that we're getting from our task before the ending brackets of where the task ends, we're not going to find anything, right? Because the task is running here, and the function is ending here. Now, the function's done, but this task is awaited. When this long-running sequence is done, then we see it, right? Now we see it. And now we get done. So this runs, we print our results, and we return done. So this returns a string when it's done. And here we can clearly see the task is running, right? We start it, the Fibonacci, the task ends, the Fibonacci starts, it finishes, and then now we can use the results, right? Yeah.
What's the difference? Can you go up a bit?
Yeah.
What's the difference in making this task closure like you did this task one, instead of like making another async function to do the same thing?
Why don't I want to make this a closure?
Oh, yeah, why not async function that basically does the same thing?
Well, okay, so what I'm trying to point out here is that task has value and has result. So,
But doesn't the return of the async function also has result?
right, but this task can throw, and it can also have, you can pass this task around to other functions that need tasks. So I'm not saying like, there's alternative ways of doing this. I'm trying to show that there's two ways to make a task. One is if you need the task for later, go ahead and use this syntax to make the task so that you can take this task and pass it around, or you can call it later with a value or get the result. So I'm just trying to show how to make tasks differently, right? So this task is very different than making this task, right? Because this task you can't pass around. And you wouldn't call dot value or dot result on it. So I'm more like just showing how to make different types of tasks. That'll come up. Okay, so here we make a task, and because it's obvious that it returns, we don't have to put the return on it. So it makes it a little bit easier. Now here we have multiple tasks, right? So I'm going to build task 1, I'm going to build task 2, I'm going to build task 3. What's really important here, right, what we've got to get our head on is I'm not going to run the tasks when I ask for value, right? This is not where the task is run. The task is run as soon as this let hits this task 1. So you might go, oh, okay, I'm going to call value, and then the task runs. No, the task is done. So as soon as you go let task 1, task is run, it's run, it's gone, it's started. So we have 3 asynchronous tasks here that have already finished. By the time I come down here and I await for my task 1, right? Now I don't know when task 1 is going to return. It's a suspension point. The operating system is going to use cooperative threading to figure out who is the highest priority for whatever needs to be done. It might never be suspended. It might be suspended 100 times. Yeah.
I don't want to jump the gun, but is there a way to define a task that doesn't run right away?
You can suspend it.
Right.
So you can make a task, and then I think you can just go to suspend, and then make it a suspending task, so that that task is not running, it's suspended, and then when you run it, you just call resume. So you can make a suspending task. I don't have an example. Make an example. Okay. So here, when we call value on here, we await for it because it's a background thread and we have to get it. But note if the 2 billion processors on the iPhone have already done it, it's done. In fact, I wonder if there's a day where we get to the point where the iPhone has so much power that we don't even worry about putting threads on the background because it's so powerful that you can have a million things happening on it and it just doesn't even use up the main thread ever. People say that when 5G comes down, you will never write another app on your phone again because 5G is so fast by the time you touch the icon, it goes out to the web, generates a new image, downloads that image, does everything on the phone before you even can lift your finger off of the icon. At that point, 5G is so fast you don't even, everything's done in the cloud. So all this stuff is like maybe just water under the bridge, who knows? But right now, there's a chance it could suspend, it's a chance it might not suspend, it just depends on what those 2 billion processors are doing. Here, we're going to try on task 2 to get the value. At this point, task 2 is ready to use. And the reason we don't have to catch anything here is because I have a throws here. And the whole reason we did the first playground collab is because I don't have to explain that because we throw, I don't have to catch anything in here, right? Okay. So that's why that try we're not even messing with it. Now, if I call result, I will get back my value and the error. So if you need just the value, like I always just need the value, I would just get it back. If I need the result, I can also get that. We can see here when we call it, let's comment everything else now. See what's happening. All right. Cancel. All right. So when we run this, we can see that the value returns the value, and the result would actually return the success. It returns success, and it returns the value. So just depending on what you need. So this is the value. This is the result. Just depending on what you would need, you could get either one of those out of it. All right. Now, one of the cool things we could do is we could yield tasks, we could sleep tasks, we could do a whole bunch of different things on tasks. Here we're going to talk about how do you put a task to sleep. So, sorry, how do you cancel a task? Canceling a task. So here we have a task, and it is a string or an error. And basically, it takes nothing and returns a string. Now, what happens is when we call it, we're going to put it to sleep, and we're going to check for cancellation, right? So this is how you want to handle tasks that are long running. If you have a very long running task, you always want to check for cancellation. Because if someone doesn't want your tasks anymore, you have to give them the ability to cancel it. And so this is what we do here, right? We start this task. We're like, oh, you know what, Mr. Task? We don't need you anymore, so we're just going to call cancel here. And that cancel is going to throw this task was canceled. And when we run this demo, what we will see is the task starts up, sleeps for a second. While it's asleep, we get a cancellation, and then we see that the task is canceled. And if we didn't do that, we get into a whole bunch of problems. Because what happens here is if SwiftUI starts a task for you, it can cancel that task when the view goes away. But if your task is not checking for cancellation, that task will keep running. The task that SwiftUI started does go away when the view goes away. Your task, my task, that is not checking for cancellations will keep running. So when we run, if we have a really long running task, say we're trying to get 1,000 images from the server in a for loop. And I'm going to show an example of using a for loop to get 1,000 images from the server in a task. What we're going to do in that for loop is we're going to check for cancellation, right? Because we don't need that for loop to continue if it's been canceled. We're just going to catch the error, and we're going to say, depending on what the user did, or depending on the situation, we're going to handle the task being ended. Yeah.
The check cancellation is on just it's a static method on the task struct.
That's how I've seen it. I haven't.
Yeah, it is.
Okay, thank you. That's how I've seen it. I always thought about that too. It's like it's not on the task. Yeah, thank you. But that's how I've always seen it written. All right. Now I just talked about for loop. What if you want to put a bunch of tasks in a for loop? Say you have 1,000 images that you want to download, and you have an array of 1,000 images. How do you get 1,000 tasks? And if you cancel one task, you want them to cancel all of them. If you yield or sleep one, you want all of them to. And that's what a task group does. A task group takes a bunch of tasks and puts them into one group, so it makes it a lot easier to handle. So here we have a group, and we're adding a task that just returns a string. Here we're returning hello from a task group. And in the middle of it, this guy returns done. Remember, he does a Fibonacci sequence, and when he's done, he returns the string done. Now, when we call this group, what we're going to do is we're going to call it in a wait that's in a for loop. This is awesome. This is a asynchronous, an asynchronous for loop. We don't know what parts of the group are going to return when. So this can come out in any order, right? We don't know. This for loop is smart enough to know that as the results from the task group come back, it's going to handle those. So here we got hello from a group, but got done at the end. Well, done is in the middle, right? It's not sequence. So don't put tasks into a task group thinking they're going to come out the same order that you put them in. They're just going to return when they can. So that was that example. Let's see here. Now, what's super, super awesome about what I just showed? I was just adding task groups. What's super awesome is when you have an array or you have some other data structure that's very large that you want to build a task on. So you could either write add task, add task, add task, and that works great. Or what you could do is you can get your array, right? You can get your array of cities here, and in a for loop, take each one of those cities and add it to a task group, right? Very efficient. There's hundreds of thousands of tasks in one task group in a for. And so what happens is now I can just tell that group to return, that task group to return to me each group, right? And I'm going to wait on each group. As each group comes back, I can use it. So if we run this, what you'll notice is, right, I start the loop. I don't know when what order I'm going to get these back in, but the loop is going to go through until it gets a termination. And then when the loop gets a termination, it's going to end the loop, and we're going to continue. So this is a really nice way to handle very, very large groups of tasks. Let's see, I want to comment out all that stuff. All right. Another really great thing about task groups is this guy here. Okay. We can call all sorts of functions on groups. We can call reduce. We can call average. There's lots of things that we're used to doing with maps that we can actually do to groups. Like here, what I'm going to do is I'm going to take all the values, and I'm going to add them all together. I'm going to reduce it to one value, and then I'm going to take all of those values, and I'm going to get the average from them. So again, not only is it a simple way to construct task groups, but I can now manipulate the values from those task groups as if it was a data structure. Makes life really much more enjoyable. And this is an example from Nick, basically just showing that. And I put this in, I put this in the playground to show how easy it is to use with SwiftUI. So again, we have our URL session where we're just going to give it a URL, and it's going to just give us back an image. And what we're going to do is we're going to put that into a lazy grid. So here we have our task, right? And our task allows us to go into a context that supports asynchronous programming. And in there, we're going to take every single photo, right? And we're going to add it to a task group. Now, after we added all those to the task group, what we're going to do is we're going to wait on the fetched image, right? So this, we added to this task group a asynchronous fetch image call. So we go to the task group and we say, okay, task group, give me back the first one in the group whenever they come in, right? Whenever they come in, I'm going to get this image and I'm going to append it to my images, which is what gives us this guy. Now, what's interesting about this is this try has a question mark at the end of it, right? And we talked about, that's why we spent all that time talking about try catch, right? So now I can easily say, if I put a question mark at the end of a try, it's like as if this function call does not throw. What does that mean? Well, if this function call is being treated like it does not throw, when it throws, we don't know because it's not throwing. We have to tell our users, if you expect 100 pictures, right, and I'm doing a try question mark await, you're going to get, there's a chance you might get indeterminate results. So we definitely want to send that back up to the user, right? So this, because it's not paying attention to any of the throwing, will bring back just the images it could find, which is great for a demo, because in the middle of a demo, I don't want pictures like the whole thing crashing. Just whatever pictures you can get on this, crazy Wi-Fi that never works, whatever you can get, give them back to me, and I'll display them. But it's really, really tricky, because if he's throwing errors, I'm never going to see it. Yeah?
So back to my earlier question, on line 384, is it Swift that recognizes this is going to go back onto the main thread, 384? So you're appending something from a thread that a task could be in whatever thread, but since it's being appended to images, is Swift figuring out I need to put that back on the main thread?
No, this is an error because the playground did not point out to me that I'm actually updating the images from this task, and yeah, I need to fix that.
Okay.
Yeah, good catch. Because anytime we want to change anything with the UI, we want to be on the main thread. But there's examples of me doing that later. I just haven't gotten there yet. But this, okay. So we're going to do 2 more playgrounds, and then we're going to take a break when we start with actors. But let me just get through these 2 last playgrounds, and then I'll let you guys out for a break, because it's already 3 o'clock. We only have an hour left, and I have to go through all actors, Sendable, Swift UI with actors, and Async. So, okay, just 2 more playgrounds, and we'll take a break. Okay, so we have a struct, which is user data, and it has a string array, int, and an int array, and an int. When we call getUser, we're going to get back a string. When we call highScore, we're going to get back an array of ints. Friends is going to return an array of strings. Fibonacci number is going to call the Fibonacci and give us back a Fibonacci of 10. Okay, now, what if I want all those to run at the same time, and I want to use all those values at the same time, right? I don't want to go await, okay, all the awaits are done, okay, now give me back everything. Super simple, right? Instead of having this be a asynchronous function, we do an asynchronous let. Now, as soon as the let hits this variable, it starts immediately, right? We already talked about that. So all these are running as soon as the let call is called. So they're all running. But I want to use these all at the same time. All I have to do is write await on it. That's it. Super clean. And what this is saying is, I know that all these are asynchronous calls, but you know what? Just wait until they all come back, and then give me my user. So here, when we call user name, that is independent, we're going to have user, and we're going to be able to use it in this knowing that it awaited and it's all done. Now, this user is created when we get all this information, but the user, the get user has already run. It already finished up here. So it already finished up here, but to make that user struct, we had to await for all of the pieces to come back, and then we can use it, right? Now, what if it throws an error? Again, we don't have to write try, await, try, await, try, await, try, await. No. We set it up to be just one try, await for the whole thing. And then once this finishes, it either throws or it prints. And so if you have a bunch of tasks and there's one data structure that needs all of them, this is it's a much simpler way to get all that information you need to be able to populate that struct. And then we're just going to do one more, and then we're going to take a break and we're going to come back and talk about actors. So, okay. I've been talking a lot about how wonderful Swift structured concurrency is, right? And I'm telling you, if you can use it today, use it today. And you can tell me, no, a lot of the functions I'm calling are using continuations. I'm saying, well, as of WWDC 2020, Apple has said pretty much anything you can call with the continuation, you can now call asynchronously. And then you go, no, but all my libraries are still taking continuations. We have a solution for that. And the solution for that is, if we have this fetch latest news, and it takes a closure, right? We want to be able to not have our users of this library have to send us a closure. We want them to be able to use async await. And the way that works is this function call, I'm going to call from inside this with check continuation, right? So this function call is this function call. My users are going to use this function call. So my users went from having to pass me a continuation to just using it asynchronously and getting back a string instead of having to pass me a closure that returns a string. Okay, so this is a much cleaner signature than the one we had. And the way we create this is with check continuation. We get this continuation, and we pass this continuation to our function that requires the closure. And so what happens is the items that would normally be generated are now given to this continuation for this thing to resume on. And what's really nice is when you call a function like this, you might never even call this completion. You might call it multiple times, right? There's a whole bunch of issues that come up when you pass this closure to this function. The compiler does not check in any way. Did you call it? Did you call it more than once? It doesn't. But for Swift, actually it checks that this continuation is called once and only once. So here, when we call this function with this closure, right, we know that it is being done properly. When we call this function with this closure, we have no idea if it worked. If we called the completion once, called it 100 times, forgot to call it, we don't know. But not only is this easier to use for us as API library designers, but it is also safer for us to do. Yeah.
Are continuations cancelable?
So when you get this task, when your user uses this task, he cannot tell it's not a normal task. He can call .cancel, .yield, .sleep. He can do everything with this task. We've been talking about tasks. It's a regular task. And you can control it as a regular task. In fact, a lot of Apple's synchronous calls are just using this wrapper, but we'll never know that.
Well, would we have to then go into the closure-based version and figure out how to cancel it?
No. No. You just wrap it. You wrap it like this, and when I call you, like you give me this library, when I call this, I can't tell it's not a normal task. No difference. Yeah. Okay, right. So, now, almost done before we take our break. I have this asynchronous print news that returns an array of strings, right? When I call this print news, and I want to get the fetch latest news, I can't tell that it's been wrapped. I can't tell any, it just looks like a normal asynchronous call to me. I just call await on it, and I get my items, right? Super clean. Trust me, your users, when you're building your libraries, are going to be so thankful. The last iOS app I wrote, every single API call that I had to closures, every single one is now, I can just do await on it. I don't have to pass in a closure. So much nicer. And if it throws, I just catch it. Life is so much better. No more pyramid to do. No more wondering, did I catch the cancel? Did I do the continuation? Did I do it twice? Did I forget to call it? No, super clean. And then here, we just get those arrays and we print them just like it's a normal day. Now, Nick provided some more examples here where we have this get data, and he's wrapped it around the URL session that, the old URL session. So he's wrapped it, and instead of calling it the old way, we can now use sorry, okay. Apple, rewind, start over. Apple, like I just mentioned, has taken a lot of API calls that used to be taking in closures. They just take the asynchronous method. Here, we see that we can call URL session and just await try for it, right? Before, we had to send in this data, right? And so it gets kind of crazy to figure out that what is happening in here, right? Here, if my data is good, I can go ahead and resume the continuation. If I have an error, I have to be able to handle it. But even, if there's any other errors, I always have to make sure that I call that continuation once and exactly once, right? This is where we get into all sorts of nastiness, like I was mentioning before, about making sure that the continuation is called properly. And this resume is actually on this task and not on the continuation. And you have people going, well, what's this resume? What's this resume? No. We're done. All we got to do is call try or wait on URL session, and we get our data. And we can just use our data, turn it. Here, we get into all sorts of continuations and how many times did I call it? Did I forget to call it? Did I call resume? All that. No. And here is an example of getting an image, right? So we get this image, and what we're going to do is we're going to return the URL and go back onto the main thread and just print that image. So, okay, one last example for you guys to experiment with when you start playing with this. It's not called that, it's a playground. When you play with this playground, we have get an image from a database, which takes a closure, and what we're going to do is we're going to wrap that with a continuation. So we're going to call this here. This is the continuation we're going to pass it. So for us, we're just going to be using this asynchronous call instead of having to deal with this nightmare. And so when we call it, we're just, all we have to do is call await, and we don't have to worry about any passing in closures. Okay, I need a break because I think my brain's fried. But when we come back, we will talk about actors, how actors work, Swift UI with async, and then why combined is probably going to be replaced with async algorithms and async streams. Okay, let's take a 10-minute break. So we'll be back at 3:25, which will give us just enough. Okay, why do we need actors? The reason we need actors is because we're going from a single-threaded idea to a multi-thread idea, and we're going to be working with the heap, right? So what we see here is anything that's put in the stack is, just think of it as immutable, right? And that's why whenever we do programming, and that's why Haskell's amazing, right? Everything in Haskell is immutable. People love to do threading programs with Haskell because there can never be any problems. It's all immutable. If you want to make an array and you want to add one thing to the array in Haskell, you make a whole new array, add that one thing to it, because you can't add something. So it's completely immutability. We always want to work with immutability. Structs are amazing. They're immutable. You never have to worry about a struct, right? When we start talking about classes, we have to worry about them. They're shared. Every single thread is going to use the same exact class. And thread reentry is difficult. Shared resources inside of a class is difficult. But with actors, it fixes all that. The concept of actors is not new. Basically, the underlying idea of an actor is we do not share memory, we share messages, right? That is the underlying idea between a class and an actor. And it's the same for all languages. So all languages, Swift is the only language, it's the only popular language that has actors. So for the first time in history, a popular language has actors. But actors have been around for a long time. And the whole idea of an actor is you don't share memory, you share messages. So Swift actors, we're going to share messages and not memory. And that, therefore, when we have a bunch of threads going through an actor, there's no contention. So the reason we need actors is sometimes we have to have a shared resource that's going to be multi-threaded. All right. Now that we've gone through exactly why we need actors, we can start talking about what is an actor. Oh, and all this is being screen captured, my voice, the slides, and everything. So if you miss anything, you can just go back and watch it again. Okay, so we know we need actors because it's a shared resource, and we can't have a shared resource with multiple threads. Need to make this crystal clear, so we have this playground. Same exact code, one is a class, the other one is an actor. The class is called a risky collector because it's going to fail. And the other one is called a safe collector because it's always going to work. So the class, this is the contrived idea I came up with work from Nick and Paul. I kind of put it all together and tried to explain the best I could what's happening here. Class has to have an initializer, right? A struct doesn't. So here, we're going to get the name of the risky collector and a set of strings. We're going to pass those in. We have a send function where we can send something in our array of strings to another risky collector. If it works, we get back true. If it doesn't work, we get back negative if it transferred. Now, we're going to write this code really sloppy so that it fails. You don't have to write it this sloppy because there's other ways you can construct this and it won't have this issue. But we're going to make it sloppy so we can get an issue. We're going to check the array of strings and say, does this array of strings have the string I want to send over? If it doesn't, then we're just going to say, you know what? We don't have it, and we're going to return false. If it does have it, then the guard allows us to go down the happy path. I love the happy path. I was designed for the happy path. Okay, happy path. Happy path says we do have it, and it's going to this person. Then what we're going to do is we're going to remove it from our deck, and we're going to transfer it to the new person, right? So here, we say that the did transfer worked, and we then transfer it to the new person. So we remove it and then transfer it, and we're happy. The problem with this is, once I get into the happy path, that's a critical section. If I have two threads that got into this send exactly at the same time, they both come into this exactly at the same time, and they say, do I have it? Well, it's going to check that both threads are going to say, yes, you do have it. And they're both going to come down here and say, I'm going to pass it to this person. The right way to program this is, inside the remove, I give it to the person. So if I move this transfer to the inside of the remove, I won't have any problems. But I made a critical section for myself here. After the guard, I do no more checking. I don't check to see if it's multi-threaded, if I still have it. I say everything's good. So if two threads get into here, they're both going to call remove, and they're both going to call transfer. Not a good situation. So let's see what that looks like when it runs. How do I run that? Okay. Okay. So sorry, I have my transfer, and I have ability to print the deck. My safe actor. Okay. So I start off, and I make my first risky collector, whose name is Sam. He has a deck. All of these strings are in his deck, right? The other guys have nothing, have absolutely nothing. I'm going to use Grand Central Dispatch, and I'm going to send two threads through the same code at the same time, and it's going to cause a problem. If I put a sleep here between these two threads, they won't both be in the critical section at the same time, so I'm not going to have a problem. But then we're going to look at the deck that they all have after they're done running. So I'm going to fire that off, and it's a timing issue. They both have to go through at the same time, and they both have to see that it's not, that the deck has it for both of them. So here, we start our risky thing. We say we're going to send to Tim, in this dispatch. At the same time, right, at the same time, we're going to dispatch the other guy to Adam. The deck says it has a card for Tim. The guard statement, this is the guard statement. The guard statement is, I have a card for Tim. The guard statement, at the same time, through another thread, is saying, I have the card for Adam. He doesn't, right? Because he's transferred the card, the card to Tim, right? He doesn't have anything for Adam, right? He's got nothing for Adam. But if we look at Adam's final array of strings, he does have it, right? Because in the critical section, we transferred it to him. If we were to put it, if we were to put the transfer inside of the remove, we wouldn't have this problem, but we didn't do that. So here we are. Both threads hit the guard at the same time. They both got through the guard at the same time. The first time that we tried to remove the string from the array, it worked fine. The second time we tried to remove it, we couldn't because it wasn't there. But both times we were able to give it, we were able to give the item to both of the risky collectors. This is a huge problem. Say it's a Ferrari or a Lamborghini and the car costs hundreds of millions of dollars. Well, we just told two people that we are going to give them both this Mercedes-Benz or whatever. Really, really a bad idea. And it's all because of our guard statement. Two threads went through this guard statement at the same time. They both got into the happy path at the same time, and they both called this transfer when they shouldn't have been able to. Now, an actor fixes that. All I did was I changed the word class to actor. And what this means is when we have something in the heap, this class, which is now an actor, will only allow one thread to go through processing at any one time. Everyone else has to wait outside for that actor until the current thread is done, right? Now this brings up a whole host of issues because you took a multi-parallel system and you're forcing it to go through one actor. This is a point of contention. You want to be really, really clever about putting your actor lock on maybe just a part of the class, or maybe just on a function, right? Look for the critical section of the function and just make that one running on the actor, right? And I'll show how to make global actors and all that, but you can put on an entire class, you can make that the entire class an actor, or you can make a part of it, a function, an actor. So really scale it down as much as possible. And that way, all the other threads are running through, they're not being constrained at this one piece of the code. So we have this thing, and I put it on the entire class. I made an entire actor, but maybe for the next one, I'll just do it on the send. So you can see, like, the send is doing most of the work. So here, maybe I would put it on the entire class because there's nothing else in here but the send. Okay. So what does this do? This, again, we see that it's the same code. It looks just like a class with an init. It's not a struct, right? It's a class, an actor. So we have the send, and we're going to send it to a person, and we see that the send is asynchronous. This means you have to await here. All of the threads that are coming into this send, they have to await for no other threads to be in this send when they go through it. That means when you're calling this guard, you're the only thread calling this guard. Can't go wrong. Nothing can go wrong. There's no critical section here. You get into the happy path, you're in the happy path. Then we do the transfer and everything else is fine. I'll talk about non-isolating and dynamic in a sec, but let me just go through the example. So, okay, this time the code is much cleaner, right? All we have to do is we have to say await on the send, await on the send. We're going to give the $1 billion car to Tim. We're going to give the other $1 billion car to Adam, and we're going to await. Now, when you run tasks, like if you went task, you went 1, and then 2, 2, and then you went 3. Those tasks, they run in sequence, right? So the first task is going to be fired off, then the second task is going to be fired off, and the third task is going to be fired off. A little bit of difference in those times. So to mitigate that, I didn't put calling both of these guys inside the same task, right? Because I want those tasks to fire off exactly at the same time, so I made them their own task so they fire off at the same time, just to prove without a doubt that they're running in sequence. But whoever gets to the await first is going to have to, it's going to run, whoever gets to the await second is going to have to wait, right? So even if there is, they're coming in at the same time, on the same, being called from 2 different tasks, they're not going to be able to get into this code, this actor, if there's another thread working in there. Now, if I put a sleep in here, this breaks everything, and the actor will now break. Let's see here. Now the actor breaks. Why am I seeing this? Save. Okay, let's get rid of this. Okay, so now the actor breaks. What we see is we sent Tim the safe car, and we sent Adam the car. This is called thread reentrant. And if you watch any of the WWDC async task talks, they talk about this. And one, try to reorganize and re-architect your codes that you don't call a wait inside of an actor. Because when you do, you have to be really careful. What we're saying here is this actor is going to yield at this suspension point. That means that the environment around that actor can change while this particular thread is at this suspension point. So I have one thread that comes in, and it's waiting on something. Another thread comes in, and it's going to change the environment that that actor is living in underneath the first task that's asleep. And if you're going to do an await inside of your actor, you have to make sure that your actor is thread reentrant. And WWC's videos, they talk about this a lot. For me, I've never had to worry about this because I can usually architect my repository or my service or whatever I'm working with that needs this actor to do a contiguous block of work and then return to me something instead of having 2 actors that need to work or something that's going to put a wait in there because of thread reentry. And again, we see everything works perfect as soon as I took out that task, that sleep in there. I'm going to let the WWDC talks get deep into this topic because one, I think every time I've come up against this, I was able to re-architect the code where I don't need to do this. and two, it's more of a threading, understanding, threading more than structured concurrency, because this happens in any language, in any model, when you have actors doing things like this. So it's more of a global issue that threads in sleeping actors have to be reentrant. But I just have to point out, threads in a sleeping actor have to be reentrant. Okay. So that's this playground. Yeah, not color. This playground is here for you guys to play with. So you can play with the timing, play with one actor, making one an actor, making one a class, and just playing with it. In fact, when Nick did all these examples, he did them in an application, and I moved them from the application into a playground just so you guys can spend time playing with this stuff and not having to worry about running an entire application to figure out what a class does and what an actor does. Okay. The next collab we're going to talk about is, remember when we talked about structs, actors, and classes? Here, in this playground, just a collab. In this playground, what we have is a class, a struct, and an actor. And I don't care how many thousands of times I run it, the actor and the struct will always return 0. Why do they always return 0? Oh, and the actor takes much longer than anyone else to run. So when you run it, you can see the class comes back instantaneously, the struct takes a little longer, and the class takes forever to finish. But the class always returns something. So what's going on here? Okay. I always like to pose a question that engages the audience. The way this code works is we have counters. And these counters increment and decrement, and they can return a value. Now, if we call these counters, if we call increment and decrement exactly the same number of times, we should always return 0. But if there's thread contention, right, what will then happen is two threads will try to increment the count at the same time, and you'll only increment once, because two threads, he said, I'll make it 1, at the same time he says, I'll make it 1, right? So inside these two classes, this guy makes it 1 and this guy makes it 1. That means the number of decrements is now off of the number of increments, and we don't get back 0, right? And depending on how far those classes, those increments and those decrements get from each other, we can return with 2, or even higher. A lot of times they return 0 because we don't get the contention that we really want to get. Oh, -2. Okay, so I set up this playground so you guys can play with this, right? So we want to just have the same number of increments as decrements. And we want to do these in detached tasks. So we have a class counter where we're incrementing and decrementing, and we're going to do this 100 times. So increment, right? Increment, decrement, decrement. These two are in a detached task. These two are outside a detached task, and these two are inside a detached task. But the only thing that matters is the number of increments is equal to the number of decrements, right? That's all that matters. So when we run this thing, it should come back to 0, right? It should come back to 0 because every time I call an increment, I also call a decrement. The problem is there's a lot of thread contention happening in here between these hundreds and these detached tasks and all this stuff going. A lot of times it comes up 0. A lot of times it comes up 0, but a lot of times it doesn't. Well, okay, maybe a lot of times it doesn't come up 0, but anyway. So what do the other guys do, right? This is a struct. Every time I call increment on the struct, I'm actually not even incrementing the struct. I'm destroying that struct, right? And I'm making a whole new struct with the current count. So whatever this struct is thinking it's doing, it's going to always return 0 because no matter what these detached tasks or whatever they think they're doing does not matter, because there's only one struct. And you're not going to get that struct wrong. There's no contention to exist. So this guy always returns 0. It has to. And this guy has, this guy is not, the class has not even hit 0 once. Wow. Almost starting to think there's a bug in the code. Ah, there we go. Okay, now the actor takes forever to run, because every time you put a detached task into the actor, where's our actor? Actor count, right? Every time we call our actor count, when we call increment or we call decrement, what's happening is if there's any other threads in there, they gotta wait. And so the actor takes forever to return. And that's just a function of it stopping all these threads. There's like 100 times we're calling this for loop, sending in detached tasks. So basically,
Technically, you're sleeping for 4 seconds as well.
Yeah, those asleep too.
Oh, yeah.
Sleeps out though, and it still takes a while.
yeah, so true. It's so true. I am sleeping, but trust me, you start working with actors, you feel it. You feel it. You're like, where's this thing going? Well, it's stopping all these detached tasks. They all have to wait to get to these methods, right? Every single time these guys are trying to get to something, this guy is.
Why is the for loop like 10 for the actor and 100 for others?
Because this guy takes forever to run.
It's like more than 10 times slower.
It's super slow. Every time that you want to touch the actor, it's got to wait for any other thread that's in there to finish, right? So I think I made these. Yeah, I made these 100. I made that one 10 just because I thought, it just took too long to finish. The other guy, yeah, 100. Yeah, sorry, yeah, yes. Oh, you got -1 this time. Funny that. Okay, so the only reason I set this up is not for me to play with it; it's for you guys to play with it. So you can play around and see how much. You could put a timer on the actor and see how much time it takes, and start 1,000 detached tasks and see how it handles the actor. All right. So it's 4 o'clock. I think what I'm going to do is talk about Sendable. No, I'm not going to talk about Sendable. I'm going to talk about Swift UI and sequences, and then I'm going to let you guys play with the playgrounds. So trying to be cognizant of time. Okay. Yeah. The most important thing I can tell you guys is we're looking at the tip of the iceberg. And I'm trying to prove to you that we're looking at the tip of the iceberg by talking about Swift Structured Concurrency and Swift UI. And then I'm going to put a cherry on top of the iceberg by talking about Swift sequences and Swift asynchronous algorithms. Because WWDC 2027, Apple is going to take this stuff and just run with it. So not only do we have Swift Structured Concurrency to play with, but we also have it in Swift UI. So let's talk about this really quickly. We have a at every second asynchronous call. We have a global actor, right? And so every single time someone wants to use this actor, they're going to have to go through one at a time because they're going to have to wait for this actor. This global actor is using this managed data actor. Okay, so here we have the @global actor invocation. This has to follow a protocol, and that protocol is when you make the other actor, it's the shared attribute of this global actor. So we have a global actor here that anyone can now use from anywhere, and it's using this actor and it's a global actor because it follows this protocol. I'll get deeper into that in a second. This is a view model that's working with the view. And anytime you're working with a view, you have to be on the UI thread. One way to get on the UI thread is by saying @main actor. So once you put @main actor on any variable, the compiler checks to make sure that that is always running on the main actor, right? So here, when we go ahead and start using this array, the compiler will check to make sure that this array is being used on the main actor. And here, we can see how to get on the main actor. When we're inside of this view model, all we have to do is say main actor.run. And this guarantees any work that we do here is going to be running on the main thread. This array, you can see here, this is the Swift UI running here. These numbers are being provided by the view model, and the view model is providing these on the main actor, so Swift UI will not complain. We're going to have an example of that in a minute. My brain doesn't fly out first. Okay. So this is our view. We have our view model, which is the @state object. And if it wasn't 4 o'clock right now, I would go through this diagram. Oop. I would go through this diagram. Oh, there we go. I'd go through this diagram because this diagram tells you exactly when you should use a regular property, @binding, @state, @observable state, @state object, or environment object. It's super easy to use. You go, is it a value type or an object? If it's a value type, you say, how's the data used? If it's read-only, it's a regular property. If it's read and write, who owns it? If it's in the local view, it's @state. If it's coming in from the outside of the view, it's @binding. Okay, that's a value type. If it's an object, right, like a view model or something, you say, is it coming in as a parameter, that's an observable object? Do I create it inside the view? That's @state object. Is it coming through the environment? Observable object. Use this diagram. Clearly shows you when you should use @binding, @state, @observable object, @state object, or @environment object. Really simple. So here, this is being passed in. Here we are creating it in our view, so it's @state object. Right? We are creating it, so it's @state object. Okay. Now, this view model has the data, this data, and all we're going to do is we're going to put it into a list, and we're going to look at it. But because we're getting this from the view model and we're using it in Swift UI, this has to be on the main thread. I'm going to give an example of what that looks like when it's not in the next example real quick. So we now see that we have a task to get the data. And we have, we have two things here. We have .task that gets a count for us, that prints a count. And we have a task that starts on a peer that does a count for us also. So when we bring this view into existence, we start two tasks in two different ways. One is a task on the view, and one is a task that is on a peer. When you do a task on a view, when the view goes away, that task is cleaned up. If you start the task yourself and that view goes away, that task still exists. So if I come here, what we notice is both tasks are running because this view is active, right? Now, if I deactivate the view, we notice that the task that I started keeps running, but the task that the view generated has stopped, right? So dot task stopped. The task I started on up here is running. The problem with this is that if my task with the 3 exclamation points, when it gets canceled, if it's doing a for loop in a synchronized way, and that for loop is not checking for cancellations, neither task will cancel, right? So when this task cancels, it stops and it sends a cancel, but that has to go to anything inside that task that it also needs to cancel. Canceling that task does not cancel all the tasks, all its children tasks. It just cancels the top task and sends cancel to all the children tasks. The children tasks still have to be listening for cancel. I was going to do that for an example, but it's already 4 o'clock and I thought we're going to be running over. So I just wanted to explain that. Dot task, the view will cancel it, but if you have a for loop in here and you're not checking for cancellation, it'll just keep running. Asynchronous. Asynchronous for loop that is looking for cancellations. But if you start the task yourself, when the view goes away, it's going to run. Okay. Just bear with me for one last second. All right. Now, in the same playgrounds, we also have an application. When you run the application, what you're going to notice is counter starts up, counter's running, and pictures are coming in. So now we can talk about what's on the main actor and what's not. We also have a zip that is a part of the asynchronous algorithms. So let me do asynchronous algorithms real quick, and then we'll come back to this. Let's do asynchronous algorithms. Okay. Okay, we're almost done for the day. Let me just do this real quick. All right. The tip of the iceberg, cherry on the top, we have asynchronous sequences, right? So what we have here is a double generator. It's going to generate doubles for us, right? And it's an asynchronous sequence, and it meets the protocol that it has a mutating next function. Now, when I call I can now call this asynchronous sequence. And the way that would work is I have this double generator, and it's super cool. When I call this double generator, I can await for it. So now I can generate my own asynchronous generators that are asynchronous, and I can wait for them. So here, in a for loop, I'm calling this double generator, and I'm going to await until I get all the numbers, right? And then I'm going to append that to this array, and then finally I'm going to print, if it's divisible by 4, I'm going to print it out. We're running short on time, so I think I'm going to just go through this really quickly. But it's in the playground, and you guys should play with this and see how you could manipulate this asynchronous sequence. But the fact that I can make a sequence that I can call for wait on is really powerful. Now, another really cool thing is these sequences, right, this double generator, not only do I wait on it, but I can call all the cool things I used to do with my data structures, right? I can treat this just like another data structure. I can say, does it contain something? I want to call reduce on it. I want to call map on it, right? So here is a asynchronous generator that I built that I can treat like I treat any other thing any other data structure I would call these map reduce functions on. And it's really powerful. So we can go ahead and I know this will find it and it reduces and it maps properly. So that is the power of asynchronous sequences, that you can use a for await, and then you can do all your map reduce functions. This year, they added something even cooler, right? Zip and merge. Zip and merge, I couldn't get them running in a playground, so we had to write an application. So let's go look at the application. Okay, we're almost done. We're going to end it in about 20 minutes or less, depending on my voice. So we have the application, which is right here. This application basically just has a content view, and that content view is 2 tabs. One tab has the image view, and the other one is a demo list view. Again, you guys can play with this when you get a chance, but it's right here. So we'll get 2 tabs. Okay. Now, the image view, yeah, it all runs inside this thing, so it's kind of cool. And zip works and merge works. Excellent. Now, the image view, all it does is, remember that asynchronous image viewer we brought up? It's just running in there. So we have that running. And we're going to see what it looks like when we call the image view not from the main task. Not from the main task, from the main thread. Okay, and we have a view model. And our view model has a couple lists and some example URLs. We're not going to talk about zip and URL yet. We're going to talk about asynchronous streams. Where is the publisher? Okay. Now, we know that we have to publish our image. Oh, it's not here. Okay. We have to publish our image and do all our work from the main actor. And that's why we have main actor here. In fact, if I remove main actor, when it tries to compile, it's going to have a whole bunch of issues because it's going to say, you're trying to use this published, inside your view model, you're trying to publish it to SwiftUI, and that's just a bad idea. Oh, sorry, when it runs, it's there. Okay, that's something else. So when I run it, we have the thread sanitizer turned on. And what the thread sanitizer is going to point out is okay, the thread sanitizer, we get to here, edit scheme, thread sanitizer is on. Okay, we'll see what's happening real quick. And then we're going to look at our view model. We had it on this string. Okay, if we run this, worked yesterday. Come here. Okay. Did you see it? Weird. Okay, I'll continue. So what we're going to see on the image, view. All right. This image view is here. We have the observable, and it's, okay. And then, let me do this. This should do it, okay. So, on this side of the preview, we have zip and merge, right? Okay. This is a part of the async algorithms. And what's happening is we have, okay, this view is this view. So this view has a body in it. And when we call zip, it's going to call this zip task. And when we call merge, it's going to call this merge task. So if we look at the zip task, what's happening is we can zip on an await, right? So again, everything that we're used to working with our algorithms, we can now do them asynchronously because Apple is moving all of their algorithms and data structures and everything into an asynchronous mode. So when I call this zip is actually the asynchronous version of the zip algorithm, and I can just await for it. And what it's going to do is it's going to get these three guys, it's going to zip them together, and then it's going to bring it out. It's going to use it in this one string. What's interesting is we're using A, B, and C. So it's going to take these three and these three and combine them zip them into one, but it can't do anything with 3 and C because this guy doesn't have a third item. If this had a third item, it would use all three. So if we run it, it acts exactly the same way zip does, except it's running on these asynchronous tasks. So if we look at send here, send is an asynchronous stream, right? Where it returns from a background task the value that you're looking for. So every single one of these guys is being sent on a background task at different times, and what zip is doing is it's waiting for the first one of this one to come through, the first one of this one to come through, and the first one of this one to come through, and it zips them all together, right? Very, very, very powerful stuff, and we get it for free because we're using the asynchronous version of zip. The timing does not matter here. This could take 5 days to come through. Zip will handle all this for us. It'll take the second one, it'll wait for the second one, it'll wait for the second one. Done. On the third one, it realizes C has nothing, and that's a null termination on the sequence. Zip end exits, and then we get our results. So if we run that, what we see is those things, this is being sent, this is being sent, this is being sent. Zip waits for them, zips them all together, sends us our first one. Again, it waits for the first item to come through, the second item to come through, the third item to come through, and it sends it. And so if we were to do this, all right, and we run it, then it'll zip all three. Right? So now it zips all three because this one didn't send the and go on forever. If these guys are live streams, then when we come into this for loop, we will never see this end zip, right? So you guys can play with that. Make a stream that is infinite. This for loop will never get the termination, and if we don't do a break in here, we'll never see this end zip. So that's it. Okay, so merge also has an asynchronous version. So it's asynchronous. Again, it's really beautifully done in that when we merge these guys, it's going to wait. Where's merge? It's going to wait for A and D to send all their information, and as they're coming in, it's just going to merge them. So if we look at merge, these two can be any length they want, right? Because we're just going to wait for each one of these individually to tell us that they're done, and then at that point, it will have finished. So if we merge it, what we're going to notice is, I did this, okay, so 1, 2, 3, 4, 5, 7, 9, and that's because I left off a number on purpose. 1, 2, 3, 5, 7, 9, 10. See, they all came through, right? So it merged them beautifully, and then when it was done, it closed the stream. Zip, merge, all these data structure algorithms that we're using. Now we have asynchronous forms of it. Now I just want to do the main actor. Okay, so I don't understand. Okay, see coming out, I even put a thing on my coming out main actor, because when I did this, the thread sanitizer, oh wait, do I have actor here? No, I don't have it here. You can either put main actor on this, and the thread sanitizer will be okay with everything you do, or, okay, you can either put it here, and the thread sanitizer will not complain, or you can just put it on the publishers, and it will not complain. So when you are doing anything that is not on the main thread.
Sorry, why would the compiler complain? Because you are calling the main actor one here.
Not compiler. Not the compiler. Sorry.
You're doing this on the main thread. You don't need annotation.
Wait.
Annotation will help you.
No.
If you don't call this actor, main actor here, then it will complain, I think.
Sorry, where are you?
You are
Yeah,
down.
down.
Yeah, more down. You're calling main actor here and appending to the zip. And it will go to the main thread.
No. Okay, so the way this is supposed to work is right here, sorry, you're absolutely right. Okay, now the compiler is not complaining. Thank you. Thank you, thank you, thank you. The compiler is not complaining. What I want to do is put main actor on this, right? Thank you. Gosh, you solved everything. Okay, watch it now. Where's my thread sanitizer? All right.
You're gonna go run zip.
Hmm?
You're gonna go click the get tip.
Oh, gosh, you guys are smart. So smart. Love it. I'm exhausted. And my throat's going out. Okay. All right, let's try that again. Thank you. Thank you, thank you, thank you. Thank you all. Okay. Boom. Thread sanitizer. Okay, what happened? Thread sanitizer is coming up and he's saying, you're trying to publish from a background thread. This is wrong, right? We don't want to see this. We don't want to see this come up. So let's tell the compiler that, hey, compiler, you check that I don't want to use the thread sanitizer to tell me I have an issue. If I do this and I try to compile it, this guy is saying at compilation time, not having to go up to this and going to the edit the scheme and then clicking here, not doing that, the compiler tells us, gotta be on the main actor. Gotta be on the main actor, right? So when I put main actor on here, compiler does it for me. It's where we want to go, right? Compiler check, compiler check. Or if I didn't want to do this, right? I could say this whole thing has to be on the, wait, hold on, sorry, okay. All right, so compiler check. Now the compiler is telling us you have to be on the main actor. Excellent. Yay. Now, what if I'm not on the main actor, right? And I want to be able to call this thing anyway. I can say this whole thing is on the main actor, right? So now this entire class is on the main actor, and the compile errors go away. And when I run it, the thread sanitizer should not bother me because I put the entire thing. Thank you for working. Okay.
You can even get rid of the main after, I think, on the properties.
Well, I would never do that, right? The reason I would never do that is because this helps local reasoning, right? You're like, okay, I know that these two publishers have to be on the main actor. So either I can make this thing the whole main actor, or I gotta make sure this is running on the main actor. So just for local reasoning, I like to use that annotation. This is a bad idea to do it because, again, an actor is slow. This is a much better idea, and the compiler will catch us. Now, if I don't do this, and I don't do this, and I do this, where's my, oh, sorry, zip. I zip. Okay. Right here, what I'm doing is I'm saying I need this to be on the main actor. But there are times when I need to talk to an actor from inside one of my classes. And what I would do at that point is I would make the global actor, oh my gosh, that's all the way over here. Sorry. Actors. Did I put it here? My brain's fried. Sorry, you guys. Okay. Okay. Great. So now we saw what main actor does. Main actor always moves you to the main actor, and the main actor is always on the main thread. Great. But what if there were other global actors I wanted to use? That's where this first global actor comes in place. And it's almost 4:30, so good thing these are in the playgrounds. You guys can go home and play with this, and play with the global actor, play with the main actor, play with the compiler warnings and all that, just make sure it's all reasonable. But I have a global actor here, right? And now, when I want to use the global actor, what I do is I say .share. I call that actor with a .share, and I'm able to get to that. Okay. Right. Where's the next one? Shared. Okay. Thank you. Here, when I'm in my view model and I need to get to that global actor, I just call it with shared, and now this is going to be running. Anytime I do anything with that manager, it's going to be running on that global actor. And that's why I must await for it. The reason I showed you at main first is because that is a global actor we're always going to be working with. And you now see how that main actor works, right? Same concept, you can start thinking about how to build your own actors, right? So these actors conform to this protocol, and then when you use it, you're going to wait for it, and then it's going to run on that global actor, and then it's going to give you back your data. And in fact, if we ran this right now, you would see that this would be running on the thread, which is the global actor. Okay, and so that's at main. That's at main actor and global actors. Okay. Let's see, did I miss anything else? Sorry, just one sec. All right. Okay, class, global actor. Okay, that's right. Main actors and publish. All right. Canceling task. Yeah, there's a little bit more in this collab that probably I'm going to leave for you guys to look at. The async stuff kind of touched on. Okay. All right, okay. My voice is going, and I'm going to hand wave. I'm going to hand wave the rest. Okay. So, all right. Last thing we're talking, because my throat's going, my voice is going, and all right. One last thing. Where am I? I'm here. Okay. All right. Okay. It's pretty much 4:30. We're going to wrap up. What I would have liked to get to, but we didn't get to, are a couple items here. One is if you look at anything about this course, what you're going to see is a lab, which is the WWDC talk, updating a class to Swift concurrency. When you watch that video, they don't provide the source code for it in an easily consumable way. So what we have here is every single one of these commits is one checkpoint in that video. So if you go back and you watch the WWDC app, update your app to concurrency, they're working with iWatch, and it's a caffeine tracking app that talks to Apple Health. It's pretty complex, but if you just look at every single one of these commits, it walks you through what needs to be changed while you watch that video to go from the original app to the final one that they did. So this makes it really easy, and this is if I had a little bit more time, this is what I was going to walk through, following that video, making this app. The other thing is, I will be doing a long blog post and a video series that you guys, if you contact me, I'll give you a way to contact me. I will share this video post with you, and it will be taking an app that does not use Swift concurrency, and I'll be moving to it. So I want to share that stuff with you guys, because that's stuff we're not going to get to.
Could you post it to the Slack?
Sorry?
Could you post it to the Slack?
Yeah.
Awesome.
Absolutely. Absolutely. Yes. So, okay. So it's 4:30. One last thought. And you guys are going to be upset because you're like, you have to cover this stuff. Okay. I will do my best to cover this in the last minute. Okay. When you have actors up here, right? You have actors up here, and only one thread can go through them at one time. But you might have to call a function that is going to interact with that actor, and so you have to make it callable. Or you might want to send some information to an actor, and it's got to be callable. What callable means is it's thread reentrant safe, right? So, okay, sorry, called sendable. I'm losing it. So what happens is, what is sendable? Sendable is anything that is not mutating. A string is sendable because it doesn't mutate, right? You can say things are sendable if you know for a fact they're sendable by marking them unchecked. So everything in here is going through this dispatch queue. So it's single-threaded, so we know that this is sendable, right? And this playground is here so you guys can play with it. But basically, what Sendable is, and at Sendable, it allows you to interact with an actor because the actor expects everything to be immutable. And when you send something to an actor and you say it's sendable, you're basically saying this is immutable and safe for the actor to use. So I think that's where I want to end on. And so basically, hopefully you guys got a really good understanding of sort of structured concurrency. And this article is here, and it basically covers a lot of stuff that we're talking about, but not in depth, but between what I said today, the screencast, and what's on here, hopefully you guys will have a really good understanding of sort of structured concurrency. And with that, I'd like to thank you. And if you want to play with the playgrounds for a little bit, I'll be around for a little bit, but this is pretty much the end of it. Thank you guys.